Okay, it looks like they got the video adapter working, so I'm going to start this, let's see, this topic on non-determinism was sort of assigned to me. There's not a tremendous amount to say, but I figure we could go through it. So in general, general distributed computation, there are all kinds of different sources of non-determinism, right? We've got disk seek times. Depending on where your head is on the disk, it'll take different amounts of time to get to the point where you want to write or read from. We've got network lag. That's a big one, you know, playing massively multiplayer online games. You shoot somebody and then all of a sudden they teleport out of the way. Message arrival order. If you've got two incoming, which one gets to you first? Clock jitter, difference between clocks on the same network. When you're reading from memory, you may have a cache miss that the data was there once, but now other things have pushed it out, and so now when you go to fetch it again, you have to reach farther out, maybe off, you know, instead of the on-chip cache, you may have to reach out a little farther to the L1 cache, or maybe all the way out to main memory. All of these things can give you non-determinism in a general distributed computation. In order to talk about some of those issues, Robin Milner in 1990, same year that the internet went online, switched from ARPANET to internet, came up with this thing he called the pi calculus, and pi is a mnemonic for process. And in Milner's view of the world, instead of having computation done on one machine and having functions composed where you put input in one side and it runs through this long composition of processes or of functions and pops out the other side, what you have is a bunch of independent programs that are running, and the way they communicate is by sending messages over a network. So his earlier process calculi were like CCS or CSP, the calculus of communicating systems and that sort of thing. It had a fixed network topology, which was pretty good for the network that they had at the time, right? They had a picture of the internet that had all 12 sites and what the links were between them. And then after developing those, he realized we can do just about everything that is possible to do by exchanging messages, so long as we're able to dynamically change the network topology. Right? And so as the internet was being built up, now you've got TCP/IP, you can open up a port. It's not just one machine doing one particular thing, but there are lots of processes running on that machine. You can get a new port there. So he modeled getting a new port by this thing in pi calculus called new, and it creates a new name that you would talk to, or a new channel. And so once you've got this idea of all of your communication happening on channels, he then demonstrated that you can embed lambda calculus or Turing machines into the pi calculus. So he showed this is a Turing-complete language, but it now allows us to do things like non-determinism. It's still idealized in many ways. Messages are always delivered. You'll never get a packet dropped. You'll never get corrupted or any of that sort of thing. Messages can't be corrupted. They're not changed over the wire. They can be arbitrarily large. You don't have data size limits. But you still have the non-determinism in the message arrival order. So you can still have race conditions. You can still have deadlock. You can have competition for resources. That's the sort of thing that pi calculus is good at modeling and reasoning about. And Rholang, language of the RChain platform, is a descendant of asynchronous pi calculus. Now, Greg's intent when we started this project was that we would very quickly implement Rholang and then implement the rest of the system in Rholang. It turns out that the virtual machine he wanted us to use was not suited to that task. And it took a long time, and in fact is still not completely translated. We're intending to use it as a JIT, a just-in-time compiler, for optimizing certain kinds of computations. But it took so long that we needed to do something else. So we wrote an interpreter in Scala, and in order to allow the rest of the system to be built in time, we wrote most of it in Scala itself. But the original intent was to do this in Rholang. Now that the interpreter has been built and the rest of the platform is built, it's very straightforward for us to turn it into a general purpose programming language, and we intend to do that fairly soon. But the design of Rholang is based on the asynchronous pi calculus because it was originally going to be sending messages over the network back and forth. There's something called the synchronous pi calculus, where you can send a message and then once it has been received, do something else. On an open network, you can never know when your message that you have sent has been received. You can wait for an acknowledgement, but then the other end can't know whether you received the ACK and so on, right? So the design of Rholang is on the asynchronous pi calculus, even though we have some synchrony that we could make use of on the blockchain if we wanted to. So running Rholang on the blockchain, the only non-determinism you get on the blockchain is the block arrival order. Now your blocks may be from an initial deployment. You don't know when users are going to come in and deploy code to the chain, or it may come from another validator that's gossiping one of the blocks that it has received to you. Say you've got Alice and Bob, they both send their gossiped blocks to Carol. Whether Alice's or Bob's arrives first is non-deterministic. If they have competing things, right, say Eve is trying to equivocate. So she says to Alice, give all my money to Dave, and says to Bob, give all my money to Fred. So then those two blocks, independent, you know, Alice looks and says, yeah, she's got money. Bob looks, says, yeah, she's got money. So they do it, they send both of their blocks to Carol. Carol says, these conflict, right? How does she decide? Well, there's something called the ghost rule, and I'll get to that in a bit. But this message order non-determinism, which one she saw first, is something that we have to think about. The other thing is that we introduced non-determinism. So because Rholang was originally designed to be run off-chain in an asynchronous environment, we chose to keep that when we moved it on-chain. Now, on-chain, I can tell when a message is delivered from one channel to another one, because all of the validators have to agree that, yes, there is this thing happening. And we could, if we wanted to, say, deliver this message, then do this, on-chain. But because we want to run it on both places, we've kept the language purely asynchronous. So we've introduced this non-determinism into the blockchain. But that turns out to help us in the end, because if we've got Alice paying Bob and Carol paying Dave, if they don't touch the same names, then it shouldn't matter in what order these blocks arrive, in what order these transactions occur. In Ethereum, it's a block chain. That is, everyone is competing to produce the next block after the latest one they've seen. There can be only one victor, right? It's from Highlander there. If you don't get it in first, then you get chopped off and you have to start over again with your work that comes afterward. Now there are some subtleties to that. There are uncles, there are lots of things like that. But in RChain, we've got a distributed acyclic graph. So blocks are added to this graph one at a time. Each validator can produce a block. What we're trying to come to agreement on is a specific directed acyclic graph. What we actually build is a larger one that contains that. So each block is going to point at multiple justifications. They say, these are blocks that I have seen, and based on those blocks I have seen, this is a valid one. But among those multiple blocks that I have seen, I'm going to choose these ones as being included in the canonical graph. So I'm choosing some blocks that I know do not conflict and basing this new block on those ones that don't conflict. So the subgraph picks out a non-conflicting directed acyclic graph inside the blocks of justifications. You can choose a conflicting block as something you've seen before, but you're basically saying, I'm explicitly rejecting that and choosing these ones as the resolution of that. When you get a block gossiped, it contains a set of deployments, that is, users have come along and said, please run this code for me, and their corresponding traces. Now, if it was purely functional, there would only be one way through the computation. Because we have race conditions, contention for resources, and so on, there are often times when you have to choose one path or another one, and so the trace tells what all these choices were. The job of a validator is to take the trace and the given program and make sure that as I follow these COM events, that they are all valid things that could happen as the program executes. So everyone has to go through the same process and rerun the code to see that it was executed correctly. And as I said before, the blocks can arrive in any order. If they commute, then we can issue a new block that we call a join block that depends on both of them. If they conflict, there's a rule to choose which one gets included. That's called ghost, and it's where the name Casper comes from, Casper the friendly ghost. It's an acronym for greedy, heaviest observed subtree. So each validator has a staking weight that, some amount of money that they have put aside to say, if I misbehave, this money gets burned. The weight of the block that goes out, traced back through all of the branches back to Genesis, gives a weight to that subtree or in this case, subgraph of the directed acyclic graph. And so using that rule, you get to choose which ones to include in the graph and which ones to exclude. So if I had that example I gave before, Carol sees give all Eve's money to Dave, or give all of Eve's money to Fred, look at which one had the heavier weight in its history and choose that one as the canonical one. So these are all the different sources of non-determinism and what we do with them in Rholang. And that's pretty much it. If there are questions about specific things that you have in mind, like double spending or equivocation or network stuff, please let me know. Yeah?
Just one clarification. So you're saying Rholang has non-deterministic execution?
Yes.
But Rholang plus this, you scroll down, plus the trace, that makes it deterministic because the trace...
Right, so the question was, Rholang has non-deterministic evolution, but then we also need to verify that non-deterministic evolution. So the initial time, at the initial deployment, the node that received the request from the client executes it once in whatever non-deterministic order it comes up with. Any execution is valid. Then it writes down that trace and passes it on, and the others now have deterministic evolution because all of the choices have already been made and they have to make the same ones. Great. Yes?
I have a few questions. One, can you go a little bit more into the justification for justifications, meaning why is it that a block doesn't just have to show the parents that it's declaring itself a child of? Why does it show a larger set?
We followed Vlad Zamfir's description in his paper. Greg asked us to use the Casper proof of stake algorithm. That was a fundamental part of that protocol. I don't know the reasons for that particular choice, but if you talk to Michael Birch, who implemented our version of the Casper protocol, or Vlad Zamfir, Tomorrow, Vlad is going to give a talk on Casper, and we'll probably go into as much depth as you can handle on that question.
Well, I can add one point to that. So the justifications, they don't just, you're giving your opinion on what should happen in the block based on what you've seen. That's one of the reasons you give it, the main reason is you can never pretend not to have seen something that you signed off before. So you cannot change your mind. It's kind of to keep you honest. You're only allowed to change your mind if it's consistent with, you get new information and, oh, now I've seen this guy's blog, so therefore maybe I think it should go this way. But once you've signed off on the reason for changing it, that is your justification, you can then no longer pretend that you didn't see something, so it makes it much harder to equivocate.
So like a block down the line, maybe you might want to equivocate, but you're constrained because you've already signed off on having seen something.
Yeah, once you've seen something, you're committed to having seen it.
In fact, the definition of equivocation is that you issue two blocks, neither of which is in the justification of the other. So as far as your blocks that you produce are concerned, it's really a tree, that every one you're producing is now a new root node, and it has to reference, either directly or indirectly, everything that you have seen before. So if you produce two things, and neither is in the justification of the other, now you have a double-rooted tree, and that is, pretending you didn't see your own block, and that is equivocation, and that's what you get slashed for as a validator. Yeah?
So is there something that gives discipline to this crazy DAG? So, right, so, it's nice that you can have different strands of the DAG which aren't one behind the other if you want to have unrelated computations. But when they are conflicting, somehow in the end, you need to choose one. So you need to narrow this thing. I don't think you mentioned, so how do we make this happen?
So Michael Birch wrote a nice article about Casper, and it includes this lovely animation of the Casper protocol working. Each validator is producing blocks that depend on previous ones. The red there is the specific subgraph of the DAG. You can see that it is long and sinuous. So it really is a chain when you view it from far away, right? That it becomes this snake-like thing. You can't branch off too far before getting ignored. So we can see like this big black part here got truncated more or less. These branches here are forks that nobody followed. And so just the natural, even random production of nodes that he did here tames it in the sense that it is picking out one long, sinuous thing that is very close to a chain. So it's not as though we're getting a very wide directed acyclic graph. It's a very small diameter graph that becomes, or at least at a particular block height, it's small diameter, but it grows long. This is just the ghost rule.
Did he run this in a simulation?
Yes, he ran a simulation and generated these images.
With the real implementation of Casper?
Yes. If you talk to Mike Birch, he probably still has that code, and you could generate your own images with it. I think Vlad's original Casper repository on GitHub also generates images. I don't know if this is the one, that this is the kind of thing that it generates or not, but I know it does generate. Oh, right, the one on Vlad's Casper gives you a timeline. It has a whole bunch of parallel lines for the validators and then bounces messages back and forth, and you can see in bold which part of that directed acyclic graph becomes the thing. This just uses an algorithm to lay it out, spreading it out as much as possible while having springs between the nodes. Yes? What constitutes a block? That is up to the validator to decide. We don't have any fixed block size. So they can receive them, and if they know something about the nature of the traffic they're getting, that it's fairly regular, they may say, okay, every minute I'm going to issue a new block. Or they may say, my traffic is really bursty, so I'm going to, as soon as I have 10 deployments, I'm going to send off a block. Or if I've just received one and it's been more than a minute, I'll send it off. But yeah, they can do that however they'd like. There's a streaming API, so the block gets chunked as it's, or at least the plan is to have it be chunked as it's delivered to the computer so that they can start working on transactions immediately rather than having to wait for the entire block if it's 100 megabytes or something. Yeah? I'm sorry. Okay, the question is, what prevents them from overwhelming the network with a very heavy block? Each deployment consists of 3 pieces of data. One is the wallet and a signature on the wallet for paying for deployment. One is a wallet and a signature for paying for continued storage, rent, and one is the data itself. So given the wallet up front that's paying for deployment, you can start reading code out of there, and as soon as that is too big, you know, that you've used up the money from this wallet, you can say, there's no way I can deploy this. You've already used up your bandwidth cost, let alone the computation cost. Right, so the equivalent, the question's what are the constraints? Ethereum has a gas constraint. The gas constraint equivalent in RChain is how much money is in that first purse for the rest of the deployment. No, it's a shard. The question is, does that particular validator decide how much is charged? And the answer is no, it's a shard-wide setting. So every validator has to charge the same amount for it, because every other validator has to run the same code themselves in order to check it. If one was charging much less, that would be a burden on the rest of the system. Yeah?
Just to clarify, that's the same amount in phlogiston, the price of it?
It's the same amount in rev. You pay in rev, and then there's a phlogiston to rev conversion rate.
So it's not like Ethereum where you get to basically set the price of computation in your transaction?
That part we haven't decided yet. It may be a shard-specific parameter. It may be one that the deployer proposes. Either way, it's fairly easy to implement. But we just barely got cost accounting in last week or week before, so we don't yet actually charge for deployments on the test network. That's coming very soon, Node 7. The initial pricing is targeted to be at about 1/3 of Ethereum rates, and they want it to decrease to about 1/10. That policy will probably apply only to the root shard, that all of the child shards get to set their own rates. The RChain cooperative has some governance issues to decide about how the root shard is going to be run. So what the fees are for the shard, what the stakes are for the shard, what rental costs are, what the computation costs are. All of that stuff is something that somebody's going to have to decide, and it's the cooperative's shard, so there's a governance question on how that's going to be set. Yep.
So one of the idea of rent is the idea that storage can eventually roll away and not be for sources if it's not continually paid for.
Right.
Does RChain have already implemented a kind of built-in checkpointing? So in Ethereum, it's a little bit stupid that in theory, so you can suicide a contract and its storage is
Yeah, we do intend to implement a checkpointing system. And the storage plan that we worked out yesterday in a developer meeting is that there will be essentially two different kinds of storage on chain. One is the generic storage, and Greg put my slide up earlier this morning that showed, hey, even at 1/10 of Ethereum's prices, storage is really expensive on chain. So we're restricting what counts as storage for the purpose of rent. And we decided that what counts as storage is that you are sending what we call forgeable data on a particular name. And we can tag those with a block height determined from the initial balance of the purse in that deployment, after which that particular term can be deleted. If you send it on a name that you can, that you've registered in the registry, that you have some way of redeploying to that name, you don't have to register the name itself, but it has to be obtainable again through something you do through the registry. Then you have a way of redeploying the thing and re-renting the same space, as it were, to keep it on chain. If you use a name that is transient, then once it goes away, it's gone forever. And so if you deploy a contract that has internally a big 10 megabyte string, that will cost you the $1,000 to $3,000 to deploy. Whereas if you just send it on a name and we put this tag on it, then it'll be a 1/10 or 100th of that cost.
And then the transaction that included that data initially, there will be some scheme by which validators don't have to retain that forever.
Right, and so then every so often there will be a checkpointing mechanism, which is basically pinching this directed acyclic graph down to a single point. You know, that it's somewhat wide, but then eventually gets to a point and spreads out again and comes down to a point. That pinching point is the checkpoint, and you only have to remember from that point onward. So you can say, here's the latest checkpoint. It's the equivalent of a Genesis block. From here on, you're good. You don't have to load everything up from the original. And that's really important because we'll be running at speeds 100 to 1,000 or maybe 10,000 times as fast as Ethereum. So it's going to grow very quickly. Yeah?
What is a failed transaction look like? If you send out, 100 gigabyte something and it doesn't work, but you still pay for it.
So the first thing you provide is the purse, right? That's going to pay for this deployment. And so that is debited first. And then you start providing data, and once you've reached your limit, if you're trying to deploy a really big thing and it's too big for what you've paid for, then it just cuts you off and keeps the money.
Okay. So, but that initial transaction goes through and you're able to...
Yes. Yeah. Because you've provided a purse and a signed transaction that justifies it, yeah. Yes? Yeah, so one of the APIs we provide, not every validator has to implement it, but they're encouraged to, is one where you can deploy code just to see what it'll do. And then each validator can set their own price for that, because none of the rest of the network has to be involved. So that one just runs it locally. You're guaranteed it'll be rolled back, but it lets you get an idea of how much it'll cost to run this thing, what the effect will be. You can even use unforgeable names there to query the internal state of things. So all of the information is public, and that's how you would get this information out. But you're not able to violate any security properties when you're actually running it on chain.
You write something where you put up a first, but then if there's not enough, send more. Or it's just the first method.
Yeah, that's one thing that we considered, that here is a purse to get the initial program running, and then it'll deposit some more to keep it running and keep going. Yeah, that's something we've considered. We will certainly implement it at some point. It will probably be a patch to Mercury, because it's only changing the deployment API. It's not changing any of the protocol. So look for it early next year. Yeah.
I have one question about the storage, about renting.
Yep.
Because there are like two dimensions of how much does it cost, what are you storing, how big it is, and for how long. And the part of how long, how is it decided? Because there is no like block time set.
There is a good notion of block height. So even though this picture here doesn't have a single chain, there's always between the genesis block and any particular block a longest path. And so for a block height to be useful, it has to increase monotonically along every path. Therefore, you have to take the longest path from, at least the longest path from the genesis to that thing plus one. And so we have a good notion of block height, and you can pay, I mean, there have been two proposals, we haven't decided which one yet, but you can pay either for keeping it for a certain number of blocks or for keeping it for a certain length of time. Since every block has a timestamp on it, that is also feasible. Yes? I'm sorry, I can't hear you. Can you speak up? The fault tolerance parameter. So the way Casper works is, as it receives messages from more of the chain, its fault tolerance increases. So you can say, assuming that at most a third of the network is Byzantine, at what point am I secure, right? So you make your own assumptions about how much of the network you think is trying to cheat you, and then it tells you at what point you can consider that finalized. If the entire network is trying to cheat you, you're done for, right? There's nothing you can do, right? But if you assume that it's at most this proportion of the network, then there are certain points at which you can become secure. Yeah, a certain percentage of the network. Yeah. Yes. Yes. Well, the root shard is trying to encourage lots of validators to get in so that it will be very secure. An unfortunate side effect is that, here's your nanometer, or here's your nanosecond, right? That this is how far light travels in a nanosecond. Let's see. Oh, I'm sorry, it's a foot, right? Because it's 300 million meters per second. You're dividing by a billion, so it's a third of a meter, which is a foot, right? Yeah. So this is a nanosecond. If you are this far away from the computer, it's going to take the signal that long to get to you. If you're kilometers apart, it's going to take that many microseconds at least to get between them. So the root shard that will have nodes all over the world cooperating with each other will necessarily be slower than, say, a shard where all of the validators live in the same data center, right? So that's the trade-off, is the security of having lots of validators cooperating versus the speed of having them all in the same place. So I don't remember exactly what your question was. Did that answer what you were?
Kind of, yeah. If we have the reality that we have all sharded, then we need to worry about the 51%.
Yes, yeah. So there's this trade-off. If you have a big collection of computers, say all the people who are willing to run validators on any shard, right? If we put them all into one big shard, it would be very secure and very slow. If we just distributed the work to individual computers independently, it would be blindingly fast because everybody's near some computer, but it would be very insecure, right? Because how do you know if you can trust that guy? Sharding is the midpoint. It's we chop up all of these computers into groups that are large enough to be secure, but chopped up into enough pieces to get some work done. So you judge the shard that you're running your contract in by those two criteria as to how fast and how secure. Yes?
There's like a DAG running on a specific shard. How easily is it to move over to another shard, back to the root if the one shard just stops?
Well, that depends on what you mean by move. You're certainly free to redeploy the contract on the other shard. They can be running in both places at once. If you want to transfer data, data is easy to move. If you want to transfer authority, that's a lot harder, right? Authority is the ability to contact, I mean, we've got this thing called unforgeable names in RChain, right? It's represented on chain as an integer, but there's no way to take that representation and turn it back into a name. So very much like in Java, you create a new object. Yeah, it's a pointer to some place in memory, but I can't give you an integer and have you turn it into a pointer and have it mean something. And you certainly can't send a pointer to an object on your computer and have it mean anything on my computer, right? So you can think of unforgeable names as being pointers within a shard. If you send a pointer over to another shard, it's not going to mean anything, right? So as long as it's pure data, you can simply redeploy all that data on this other shard. If it's got authority, if it's pointers to other objects, that's a lot harder, right? We do have a plan for that, though. In Venus, what we're going to have is shards where every validator in shard A trusts at least one validator in shard B and vice versa. That every validator in shard B trusts at least one in shard A. And the way it'll usually look is you'll have 10 or 15 different organizations, and each one deposits one computer in all of the data centers around the world that they're interested in. So your local region, your geographically near thing, has 15 different validators, none of which trust each other, so it's relatively secure, but it's also fast. And because they trust each other, if you want to move a pointer from here to there, then you can do that because organization Alice is going to say, hey, Alice Prime, was this the right pointer? And Alice Prime says yes. And Bob is going to ask Bob Prime, is this the right pointer? And Bob Prime says yes. And so if enough of them come over and say, yeah, it's the same thing, then you achieve consensus on what that pointer was, and so then code can move around. But it requires these trust relationships between the shards, and those are something that we haven't formalized and built yet, but we intend to. So. Any other questions? Yes? Yes, so there's two forms of communication between shards we might care about. There's the regional one that I just described, but then there's also this notion of parent-child shard. And the way that works is that the validators of the child shard are clients of their own shard as well as of their parent shard. So what they can do is watch for messages landing in a contract in either one, and then forward that on behalf of the contract. And the forwarding process uses a multi-sig setup so that it's not just one validator who has control over whether it's passed on or not, but rather as soon as any of those validators see that happening, they're all subscribed to messages to that contract, then they all individually send their signature on to the other one. And then once enough signatures have arrived, then it forwards it out of the mailbox contract to the other one in the child shard. So for instance, that's how Rev works. You put money in at the depository up top, the validators of the child shard see that money has been deposited, so each individually sends their signed message to the mint. When enough messages to the mint have arrived, enough signatures have arrived, then the mint creates a purse on behalf of the depositor in the child shard, and vice versa on the way out. Yes? I'm sorry, what? Is that engineering a built-in mechanism? Yes, those contracts will be deployed by default on the main network. So when you create a shard, it's essentially creating a depository and giving you a mint contract to run on your child shard such that this all happens. And the client software that is watching for those is running internally. It certainly could. It could say, please send this message down to that contract in the child shard. And so it would send it to the post office. Each validator is watching the post office contract. They each get the thing, send their copy of the message signed to the receiving post office on the other end. When enough of these signatures have come in, the post office in the child shard issues that message on your behalf. It does some computation and sends it back out. Problem is that is a very slow process compared to doing it internally. So it's probably something you don't necessarily want to do often, but could do. Yeah, that you can call down and have it sent back. That's certainly possible.
Down, back up, other way around.
Yes, you can also call up and have it returned to you. Although in general, calling up is going to be slower. Because the depository is, well, how do I put this? Anything running in the child shard is susceptible to the validators of the child shard. If you then have a grandchild shard, the thing running in the grandchild is susceptible to both the validators in the grandchild shard and the one in the child shard and the one in the parent shard. So it makes sense for validators to not only validate their own shards, but all of their ancestor shards as well. That will tend to make the leaves the fastest and least secure, and the root slower and more secure. So it's likely that they will call down to a fast shard, do a big computation there, and send it back up to the slow shard, rather than vice versa, if they're doing it cross-shard at all. Yeah? Well, it depends on how the shard is organized, right? If you are a geographically distributed shard, that it's not all running in one data center, then in order to get enough signatures to trigger the behavior in the other one, it's going to have to go across the world, have them do their signing, and then go back across the world again. Yeah, probably still faster than Ethereum. Currently, yes. Ethereum is working on proof of stake as well. Vlad Zamfir works for the Ethereum Foundation. They're trying, Vitalik has his own version of Casper. That's why Vlad calls his CBC, correct by construction Casper, to distinguish it from what Vitalik is doing. So they are working on proof of stake, and they may become orders of magnitude faster. The problem is they're trying to remain backwards compatible, and so it is taking far longer than they expected to get this thing deployed. Yeah?
How do you envision, for the shards, it's going to be pretty important for people making decisions about where they want to run their software to know something about the identity of the validators?
So we have planned a Shard Explorer that you start at the root, and then you can find out what the IP addresses and identities and so forth of shards are if they choose to make that information available to you. So if they're trying to attract customers, they may choose to make that available. On the other hand, if you've got a a business who wants to interact with the RChain network, the whole thing, but their particular shard is reserved just for their internal departments that don't trust each other or something, then they don't have to advertise that, right? Yes?
Can Shard be geofenced?
Can shards
Be
be
geofenced?
geofenced?
One say that these shards will only accept data that is coming from these regions. One say
I presume so. You'd probably have to put up a service in front of the existing deployment that would check that information and then forward it on to the API. Okay, thank you very much.